Go find me a box with absolutely nothing in it. I'll wait. I'm holding a jar. Let's say I pumped every last molecule of air out of it. Perfect vacuum. You'd look at this and say, that's empty. Nothing in there. And I'm telling you right now, you're wrong. There's more going on inside this jar this second than in most things you'd call something. Don't believe me yet? That's fine. I wouldn't either. Just hold on to that claim, because by the end of this, I think it's going to bother you the same way it bothers me. Let's start with the easy crack in the idea of nothing, the one you already half know without realizing it. Even a perfect vacuum isn't a total blank. Gravity passes right through it, bends space around massive objects, no air required. Light travels through it. Magnetic field lines thread through it like invisible wires. So empty was never really nothing. It was always a stage other things could act on. A blank stage, sure, but a stage. Something with structure, something things could push against. That's the warm-up. That's not even the real strangeness. The real crack comes from quantum mechanics, and specifically from something called the uncertainty principle, which most people have heard of, but almost nobody's actually sat with. You probably know the position and speed version. The more precisely you know where a particle is, the less precisely you can know how fast it's moving. Same rule, different pairing, applies to energy and time. You cannot know both to perfect precision, ever, not even in principle. And here's the part that should stop you cold. That's not a statement about our instruments being clumsy. It's not that our measuring tools aren't good enough yet. It's a statement about nature itself. Nature does not allow perfect stillness, not anywhere, not even in a vacuum, not even in the emptiest patch of space you could ever construct. So what does not allowing stillness actually look like physically? This is where it gets good. The uncertainty principle lets energy borrow itself into existence for a moment, as long as it pays the loan back fast enough that nobody could ever catch the debt. Specifically, a particle and its antiparticle can pop into existence together out of what looks like literally nothing, and then annihilate each other and vanish again, so long as the whole transaction happens faster than any measurement could possibly register it. Blink, and it's already both born and gone. Picture it like this. Empty space isn't a silent black canvas. It's static on an old television screen. Flickering, popping, particle pairs winking into being and instantly canceling out, everywhere, all the time, at a scale so small you'd never notice it with your bare eyes. That's not poetry. That's the actual predicted behavior of the vacuum, straight out of quantum field theory. Now, and this is the part I really want you to lean into, because up to here it might still sound like a cute thought experiment, something physicists made up to sound clever. It's not. We can measure it. Take two metal plates, bring them very close together in a vacuum, closer than the wavelength of some of these flickering pairs. And something happens that shouldn't happen if the space between them were truly empty. The plates get pushed together. A real, measurable force, squeezing them inward, with no material touching them, no air, no wires, nothing conventional causing it. This is called the Casimir effect. It's been measured in labs. It's confirmed, repeated, not controversial. Nobody in physics is arguing about whether it's real. Sit with that for a second. A force, coming from particles that by the very rule that created them aren't supposed to stick around long enough to push anything. And yet, they push. Every single time we set up the experiment. So here's where most explanations stop. Isn't that wild, they say. Empty space isn't empty. And then they move on to something else. I'm not going to do that to you, because this is exactly where the real problem starts. If empty space is buzzing with these fluctuations, particles constantly appearing and disappearing, then empty space should have energy, an intrinsic energy, baked right into the vacuum itself, even with nothing in it in the traditional sense. Physicists call this vacuum energy, sometimes zero-point energy. Fine, that's a reasonable thing to expect. So, calculate it. Add up the contribution from every possible fluctuation, every particle type, every energy scale quantum field theory allows. Do the math properly. And when you do, you get a number. And the number is insane. Quantum theory predicts a vacuum energy roughly 10 to the 120th power times larger than what we actually observe when we look at how fast the universe is expanding. I want you to really register that number, because saying 10 to the 120 fast just slides past you like any other big number, and it shouldn't. That's a 1 followed by 120 zeros. That's not off by a lot. That's not even in the same universe of wrong. If you missed a measurement by a factor of 1,000,000, that would already be an embarrassment in physics. This is wrong by more orders of magnitude than there are atoms in every star, in every galaxy you could ever see. This is, without any exaggeration, the single worst prediction to observation mismatch in the entire history of physics. Now, here's where I have to be careful, because this is exactly the spot where it's easy to fool yourself into thinking the problem's been solved. We do have a name for the actual observed effect, the tiny leftover push that seems to be accelerating the expansion of the universe. We call it dark energy. We give it a symbol, we drop it into Einstein's equations, and it works. It predicts the expansion beautifully. Cosmologists use it every day, successfully. But naming something is not the same as understanding it. I've said that before, and I'll keep saying it, because it's the easiest trap in the world to fall into. Calling the mismatch dark energy tells you where to put a number in an equation. It does not tell you why the raw quantum calculation is wrong by 120 orders of magnitude. It does not tell you what mechanism, if there even is one single mechanism, cancels out almost the entire predicted vacuum energy, leaving behind just enough, just barely enough, to gently push galaxies apart at exactly the rate we measure. Not zero, not the full absurd quantum prediction, some impossibly precise, impossibly small leftover, sitting right in the narrow range that allows galaxies, stars, and, as it happens, us to exist at all. Nobody has a derivation for that number from first principles. Nobody. We've built an entire working cosmology, one that predicts the large-scale structure of the universe with real precision, sitting right on top of a number we cannot explain. That should bother you. It bothers me, and I think it should bother anyone who calls themselves curious. So let's step back and look at what we actually did here. We wanted to know what nothing is. We looked as hard as we possibly could, with the best tools physics has ever built, at the absence of everything. Genuine emptiness. No atoms, no light, no matter. And instead of finding silence, we found the most violent, unresolved argument in the history of science. We found particles flickering in and out of pure vacuum. We found a measurable force pushing metal plates together from that flickering. And we found a 120 order of magnitude gap between what our best theory predicts should be there and what we actually observe. That jar I started with, the one you'd call empty, isn't holding stillness. It's holding a live wire. A quiet one, sure, quiet enough that you and I can sit here without being blown apart by it, but not still, never still. And here's the thought I keep coming back to, the one that actually unsettles me a little. Maybe nothing was never a real category to begin with. Not a philosophical nothing, an actual physical one. Every version of empty we can construct, a jar with the air pumped out, the space between two atoms, the vast black gaps between galaxies, turns out, the moment you look closely enough, to be full. Not full of stuff, not full of particles sitting there permanently, full of possibility, full of something flickering in and out, held right at the edge of existing, popping into being and vanishing again faster than the universe itself can notice. We don't know why the void hums the way it does. We don't know why it hums exactly quietly enough. Not zero, not deafening, but precisely, suspiciously quiet enough to let galaxies form, instead of the whole universe tearing itself apart in the first instant. We just know that it does. That's the honest answer, not a comforting one, not a tidy bow on the end of the story, just the honest one. And maybe that's the real discovery in all of this. Not that we finally solved the mystery of empty space. We didn't. What we actually did was finally find out there was one at all. For most of human history, nothing seemed like the one thing that needed no explaining. It was just the absence of everything worth explaining. And it turns out that's backwards. The emptiest place in the entire universe is the place we understand the least. And every single one of us has been walking through it, breathing through it, existing inside it, our whole lives, without ever noticing it was never empty at all.